This video presents a generic experimental procedure. Please consult your class notes for term-specific instructions. The lab setup for this experiment consists of a function generator, a power amplifier, a microphone and preamp, a standalone speaker with microphone bracket, and a speaker box with microphone bracket. Typically, only the exposed speaker is utilized in the first week. The speaker box is introduced in the second week. Here's a block diagram of the system. LabVIEW controls the key site function generator, which outputs a sinusoidal signal to the power amplifier. The boosted signal passes through a shunt resistor, which allows us to measure current flowing to the speaker. The shunt resistor is valued at 0.1 ohm. By measuring the voltage across the resistor, denoted V2, we can calculate current using Ohm's law. The voltage at the speaker, denoted V1, is also measured throughout the test. The shunt resistor is physically located at the DAC chassis, mounted in a BNC to banana jack adapter. Here's a more detailed diagram of the wiring, which also includes a microphone and preamplifier to measure acoustic pressure at the speaker. This diagram is included in the student guide. Gently place a speaker on the PVC stand and connect the alligator clips to the terminals. Note the polarity: black to the negative terminal and red to the positive. Turn on the key site function generator using the power button. The boot up sequence takes about a minute. Turn on the power amplifier using the front button. Place the stand with the microphone over the speaker. Carefully use a ruler to position the boom microphone a prescribed distance from the speaker surface. On your desktop, open the X95 shortcut folder and select Loudspeaker Main Shortcut. LabVIEW may take a few minutes to load. Once the LabVIEW program is open, activate the Configuration tab. Navigate to the Function Generator port and use the pull-down to select a valid USB port to connect with the key site function generator. Next, verify the amplitude voltage is set at 0.05 and the magnitude to ohms. Click the Frequency Sweep tab to return to the main panel. In order to determine the various speaker parameters, you'll need to run a series of 6 different tests. First, we'll perform a coarse frequency sweep with the microphone to capture the general response profile. Click on the white arrow in the menu bar. The frequency sweep sequentially steps through a range of frequencies, which we'll set from 5 to 300 Hz with a large step size of 5 Hz. We'll use the default settings of 2000 milliseconds to ensure steady state and a repetition of 1. Now press the Take Data button to start the sweep. The various signals are plotted in LabVIEW along with the construction of the Bode plots, as the frequency is sequentially incremented over the defined range. The frequency sweep will take several minutes, so be patient. When the sweep is done, LabVIEW will automatically prompt you to save the data. Enter a descriptive file name and save to the desktop. Place the microphone and stand off to the side for the remaining tests. Next, we're going to run a frequency sweep over a narrow range to better identify the resonant frequency. Use the previous results to identify a narrow band around the resonant frequency. Rerun the frequency sweep over the refined range with a small step size for improved resolution. Again, when finished, save the data to your desktop using a descriptive file name. We're going to repeat the last 2 tests, but with the addition of a mass on the speaker. Measure and record the mass of the lead ring. Gently place the lead ring on the speaker diaphragm. Navigate to the Configure panel and reduce the amplitude voltage. Then return to the main panel Repeat the course sweep from 5 to 300 Hz with a large step size. Click the Take Data button when ready. If you observe the lead ring rattling on the speaker, abort the test. You'll need to further reduce the amplitude voltage and rerun the test. Once again, we'll run a sweep over a narrow range to better identify the resonant frequency with the mass. Use the previous results to identify a narrow band around the resonant frequency. Rerun the frequency sweep over the refined range with a small step size for improved resolution. Here's a Bode plot with and without the mass. Use the shift in resonant frequency to determine mechanical mass and compliance of the speaker. Next, we'll perform a high frequency sweep to estimate the inductance, denoted LE. Be sure to remove the lead ring from the previous study. On the configuration panel, reset the amplitude voltage to 0.05 and return to the main panel. Set the range from 500 to 3000 Hz with a large step size of 100 Hz or so. Press the Take Data button to run the test. Plot the imaginary component of impedance versus frequency with the units of rads per second. Use the best fit slope to estimate inductance. The final test is a low frequency sweep to estimate the force factor, BL, and electrical resistance, RE. Set the frequency range from 0.5 to 5 Hz with a small step size. Then click the Take Data button to run the sweep. Plot the imaginary component of impedance versus frequency with the units of rads per second. Use the best fit slope to estimate the force factor, BL. Use the asymptote of the real component of impedance to estimate electrical resistance, RE. In week 2, you'll repeat the same test, but with the speaker mounted in an enclosure. Use the BNC to banana jack adapter, then connect the BNC cable from the power amplifier. Use the Velcro straps to secure the microphone bracket to the outlet port of the speaker box. Then attach the microphone. Proceed to run a course sweep of the system. The microphone is used for the initial sweep only. Afterwards, remove the microphone and bracket and gently set aside. When adding mass to the speaker, gently lower the mass through the port with the string and nut resting topside. Perform a similar analysis to determine the required parameters of the speaker box. Be sure to save your data before you leave the lab today.